I was at a dinner party about a month ago and I was bored and I was looking at the glasses on the table and I was thinking about what kind of shape is made in the gap between four touching glasses and what kind of properties it has. And pretty soon, well, 3 weeks later, let's say, I ended up with this. Now I'm going to explain today what this is, how it's defined and what it means with respect to that problem. But basically, what we're going to be looking at today is how quadrangles, that is, 4-point structures, can lead to these kind of kissing conic structures and how those interrelate and whether things are uniquely defined or not. Okay then, so I recently went to a rather boring dinner party and I noticed that there was four glasses touching each other and I started to think about the shape that is left in the middle and how would one describe this shape. I mean, calculating the area and stuff's kind of easy because it's just using circle formula, but I noticed that it had this special property which I thought was kind of interesting. It seems like if you draw a kind of square around this thing and then you draw diagonals, then pretty much those diagonals are going to touch those glasses tangentially, and the glasses are also touching each other tangentially. So this got me thinking, well, what other kinds of shapes are like this? Okay, so I wanted to investigate this phenomenon of how you can recreate this effect where you have these kind of four glasses or four CDs or whatever kind of touching each other and what kind of shape you get in between. And I was particularly interested in this idea that we have these sort of round curves, perhaps conic sections, which meet each other tangentially at these kind of diagonal lines of our quadrilateral. So I was interested in what kind of conics can do this. So the famous theorem, which says that as long as if you've got 5 points in the plane and no three of them are in a straight line, then there's a unique conic which goes through those points. So 5 points defines a conic. So I wanted to make a conic which was sort of tangential to these dotted diagonal lines. So I kind of did a bit of trickery and put two of my points quite close to each other, so that the conic's almost forced to be nearly tangential to that dotted line. And I also had this fourth black point, which I've made variable, so I can look at different kinds of conics, because it turns out that this kind of thing doesn't have a unique solution. So anyway, if we draw all four conics on, now we can start to have some fun. Each of these red conics needs 5 points to define it, needs 5 contact points, but there's only 4 blue contact points, and so there's a whole family of conics which satisfies this meeting the diagonal dotted line criteria, and we can see them as we vary the position of the final point, the black point. It's interesting to see what happens when it goes inside the circle as well, and we can get sort of hyperbola instead of ellipses and all sorts of things. We can get sort of petal shapes and many interesting things. Okay then, so I was interested in how you can do this if you just start off with a generic quadrangle. And we're going to be working in the projective plane now. So we'll think of our lines as going on indefinitely and parallel lines meeting at infinity. And basically, we do things in the projective plane because then our results are more meaningful. And they're applicable to all types of to many types of non-Euclidean geometry and such. So we start off with 4 points, and then we make this into a so-called complete quadrangle by joining every pair of points by a line. Now we have 3 new intersection positions, and we put red points there. These are called the diagonal points of the complete quadrangle. So now what we're interested in then is again constructing one of these or 4 of these sort of diagonal line touching curves, but we're going to add on an extra constraint now. So our extra constraint is that in addition to being tangential to these diagonal lines and to passing through the vertices of the particular side the shape is defined with respect to, we also must have our conic pass through another diagonal point which its side does not pass through. So let me just show what I mean. A picture's worth 1,000 words. I'm talking about this kind of thing. So this conic here is obviously defined with respect to this left-hand line. We could call it a sort of inner flex of this left-hand line. So what features does it have? So we call these lines sides. That's just the language of complete quadrangles. So we'll say we'll draw a conic about this side. And so what exactly are we trying to do? Well, we want to find a conic which passes through the 2 vertices on its given side, and also notice that there's going to be only 2 diagonal points which don't lie upon this side. Given any side, one of the diagonal points is going to lie upon it and 2 are not. So we're going to have that the curve passes through one of these diagonal points and is actually it actually has a special relationship with the other diagonal points in the sense that these 2 tangential lines from this diagonal point passing through these vertices just kiss this conic. So in this case we get an ellipse, and the interesting thing about this is that this is actually a unique situation. Given these constraints, there's actually only one conic which satisfies this. And so here's another one. But what gets interesting now is when you start to draw more. I mean, what's going to happen at this side? Well, let's see. We see now we have to have a hyperbola because it has to go off to infinity to come back in order to meet this diagonal point, which is the only one accessible to it. And similarly here. And so already things are looking pretty interesting. If you imagine walking out from the diagonal points inside this finite-sided quadrilateral towards this flexed edge, Well, if the lines to your left and right are converging, then a ellipse is going to get generated. However, if they're diverging, then a hyperbola is going to get created. Okay then, so let's try and rigorously prove the uniqueness of, fairly rigorously prove the uniqueness of this special kind of conic. So how are we phrasing our result? We're saying that given a complete quadrangle with vertices A, B, C, D, and given a side CD, and given a diagonal point G, which is not on CD, there's going to be a unique conic which passes through C, D, and F. So there are three diagonal points, one which is on the line CD, which is called E, which we don't think about very much, and two others, G and F. And we want our conic to pass through F, and we also want it to have the property that it goes through C, and at C it's touched tangentially by the line GC, and our conic goes through D, and at D it's touched tangentially by the line GD. So we claim that such a conic exists, and we claim that it's unique. So existence is fairly easy to prove. Okay then, so to prove the uniqueness, we're going to use a result from Coxeter's book, Projective Geometry, the second edition. So he's got theorem 8.41. A conic is determined when 3 points on it and the tangents at two of them are given. So what we want to do here is we have a complete quadrangle with vertices A, B, C, D, and we have these two diagonal points G and F, which are not on the line CD, and we want our conic to pass through CD and F, and we want GC and GD to be tangents to our conic. So using that result I just claimed from Coxeter, picking our 3 points as C, D and F, we know there's a conic passing through those 3 points that has these lines GD and GC as their tangents. So that claims there is a conic like that. I claim that just because of the structure of A, B, C and D, there are other points which must appear on this conic, and they must appear in specific places defined by where A, B, C and D are, and there are at least 5 of them, and so by the result that 5 points determine a conic uniquely, it turns out that this condition in this blue box, the theorem, determines a conic uniquely. That's my proof strategy. So let's see how it goes. So we'll draw red lines through these diagonal points. The third diagonal point is E, that's off to the right and it lies on the line CD. And then we'll mark these places where diagonal lines and sides meet. And then we'll make these green lines through those new points and the vertices of the side we want to flex. And that gives us the ability, you see, from that other green line, we got point L, where this green line meets this line AB. And then drawing back from point L down to point F, we make this cerulean blue line, and we can note that this now touches the conic at a new point O, and we can carry on and do just the same construction at the other side, and now we actually have 5 points on our conic. And so there is only one conic which passes through these 5 points, and you should notice that these 5 points, well, I mean these extra 2 points inscribed on the conic, which we've just constructed, are made by purely straight line constructions, without referring to the conic at all. And in that sense, those points must exist, must lie upon the thing, and therefore since these points must lie on the conic, these 5 points must lie on the conic, and then the theorem says that there's only one conic that goes through these 5 points. The 5 points implies conic theorem. Excuse me, I'm getting tongue-tied. And then that basically proves our result. Okay then, so I'm going to show you the process by which we can construct one of these kind of edge-kissing conics. So we've started out with just 4 points, and we've laid them out in a sort of generic way, and we're going to use them to make a complete quadrangle. So it's important, the only stipulation we have for these 4 points positions is that no 3 of them should lie upon the same line. So as long as we've got that, we can make this complete quadrangle, and we do that just by drawing all the lines between pairs of points. And you see how this creates 3 new places where these lines intersect, and they give us our diagonal points. We're going to create this conic using the diagonal point G, and it's also going to be going through the other diagonal point F, and it's also going to be going through C and D, but it's going to have a special property that these lines through C and G and the line through C and D are actually going to be tangential to the conic. For those of you that know about the theory of polarity, that essentially means that the line CD will actually be a polar of the diagonal point G under this kind of setup. So how does it work? Well, once we've got to this point, we need to get more information. So we can draw in these red lines connecting these diagonal points. This gives us what's called the diagonal triangle. And we can see that there are now more places where black points and red points intersect. And so we'll mark a couple of them out. We'll mark one here. We'll draw out this green line. Now, this green line intersects with this top line AB. And now let's construct some more points. Well, what we can do now is we can find a point which is on the conic. We rule this orange line through C and J. We find the intersection point K. And now we've already got 4 points on our conic. We know it's going to go through K. We've proposed that it's going to go through this other diagonal point F. And we know that the conic's also going to go through C and D. So we just have to find one more point. How are we going to do it? We'll find this intersection point here. H of AD and EF, well, we can draw another green line and we can also draw this blue line here, which goes between this point F, which is on the conic, up to this point J. The important thing now is that the place where the cerulean blue line and the green line cross, we can put a point there, L, and now all we have to do is choose C, K, D, L and F as our 5 points, and we get our conic. So this conic has lots of nice properties. Let me just play around with it a bit to try and convince you that it's robust. Okay, so I've messed around quite a lot with the points here, but you can still see that this conic indeed passes through this point F, and these lines GC and GD are still tangential to it, and it still passes through C and D as well. And that will always be the case no matter how much you mess around with this. So if we go back to something like our initial configuration, if I can get it back, you might notice that, I mean, there's something, I sort of think of this as a sort of, as if it was a sort of flexing of this edge CD towards the center. And since one can do this construction across each of these different edges, one can get this kind of flexing on every side. So anyway, I've basically just showed you how to construct one of these things. And now is exploiting this 5 points theorem, which is quite famous. So remember that theorem says that there is only one conic which goes through these particular 5 points. Okay, so now we're going to have a look at some interesting connections between this setup and other famous properties of conics, in particular the Brianchon point. So if you notice these important lines which go through O and D and L and C and K and F, they all happen to meet at this point N, which somehow seems special, like a kind of central point of this ellipse or something. And it turns out that it is actually a special point. So Brianchon's theorem says that if a hexagon is circumscribed about a conic, then the 3 diagonals, that is, the 3 points that join opposite corners of the hexagon, are concurrent. They're going to meet at a single point. So how do we draw a hexagon about this conic? How do we make it circumscribed about a conic? Well, firstly, we're going to draw some extra lines, some tangents down there. We're going to start to draw these lines through this proposed Brianchon point, we're allowed to do this because we're just trying to find it, so we can guess where it is a priori. Um, and we're going to go through these places which are basically linking tangents to the places, to the points, to the 6 points we've already got. So there we go. We've essentially circumscribed our hexagon about this thing. Let's just make it very blatant. So you can see this is very blatant that this hexagon has been circumscribed about our conic, and all of these diagonal lines are meeting at this Brichon point. So this is a fairly dramatic property. Okay then, so now let's move on to the dual of Brichon's theorem, which is Pascal's theorem. If a hexagon is described in a conic, the three pairs of opposite sides meet in colinear points. So let's have a look at this. To set up for it, we'll draw some extra lines in so we can make our hexagram more easily. So these are properly constructible lines between points already created by straight edge. And now we can start to construct our hexagram. In this case, it's just a standard simple hexagram, but doesn't cross over itself. But you see, the point here is that if we take any pair of opposite sides of this hexagram, let's say DL, and what's the opposite side of that? OC. Well, those sides obviously meet at a point. Here, this unlabeled black point. Okay, so now if we take FO and the opposite side to that on this hexagram, which will be DK, now let's extend out those sides. So that would be this blue line and this yellow line. Let's see where they meet. And they also meet concurrently at another point on this line. So the kind of magical thing is that in this case Pascal's line is actually the line AB itself, which is quite remarkable. When we started doing this construction, basically about this side CD, and then it turns out that the Pascal's line generated is precisely the opposite side to the one that we started to work about, which I think is quite a remarkable result.